Good morning, everybody, or good evening to people who are in Korea. So welcome back to our second lecture of Series 3 of IPAC 2025. Today, we are so happy to have our main organizer, which is Jim Hackman, to give us a lecture on the second lecture of the alpha chromatic symmetric functions. All right, Jim, go ahead.
Well, I'd like to thank the other co-organizer for inviting me to talk. I did not self-invite, at least I don't recall doing so. And so Masu did a really nice job of motivating the study of the alpha chromatic, which depends on this parameter alpha, a dict path pi, and a set of variables x, and parameter q. Okay. And this can be defined in terms of LLT polynomials. So this is the single cell LLT according to that dict path pi, and we do a plothistic substitution in here. Alpha minus x q, and then divide by q minus 1 to the n. So today I'm going to be talking about two techniques which you can use to obtain combinatorial formulas for this kind of plothistic substitution. One is superization, the other is what we call the XY technique. And in some sense, the techniques are maybe just as important or more important than the actual results we'll obtain. So part of the idea here is to have this kind of an interactive talk. If there's any issues or questions about these techniques, just feel free to interrupt because this is a good opportunity to learn them if you haven't already done so. Okay. Okay. So superization.
Jim,
Yeah.
uh, the exponent in the denominator
Yeah,
and the exponent alpha in the numerator.
it doesn't look like it's not a very good n.
Okay. Thank
So
you.
here, n is this positive integer and pi is a dict path of length, well, from 0, 0 to nn, which never goes below the main diagonal. So something like that. And handwriting's not great normally, but on an iPad, it gets worse and worse. This is just review notation. So LLT pi is going to be the sum over all words W in C plus to the n to the inv pi of W, and then what we call x to the W, which is x1 to the number of ones, x2 to the number of twos, and so on to W. And this inversion statistic, uh, it, oh, I lost my colors. Oh, here they are. So, for example, ooh, sorry. So that square with the dot would give a Q contribution if W3 was bigger than W5. So that would contribute 1 to this inv. So this is kind of a very important symmetric function known to be Schur positive. We don't have a combinatorial interpretation for the Schur coefficients yet, but these things arise in the shuffle theorem and the modified McDonald polynomials and so on. And if you do this plothistic substitution in there, you get the alpha chromatic. If you let alpha equal 1, you just get the usual chromatic, which Shrisian and Wax introduced, which itself is a Q analog of a symmetric function Stanley and Stembridge studied and conjectured was E positive, which has recently been proved by Nikita. But we don't yet know if the chromatic is E positive with the Q, conjectured to be. Okay, so we're going to be looking at expansions of this chi alpha into various bases, the Schur basis, the monomial basis, and also the fundamental quasi-symmetric function basis. And then in addition to those, the coefficients in those bases, we want to kind of study the expansions of those coefficients in these bases. And as Masu covered, so this is over K between 0 and N. And often the coefficients in these particular expansions are themselves non-negative polynomials in Q. That's kind of the motivation for these. Okay. So first idea, superization. So we're going to be working now with two different alphabets, a positive alphabet A plus, which is positive integers, and then a negative alphabet A minus, which has a bar over these integers. And we want to be able to standardize a word W. And for example, so a standardization of a word is a permutation, which is order preserving. So in a left-right sense. So the ones here are the three smallest numbers. And so what we would do is kind of, so I'll write the standardization below here, actually. Below the ones, we put the numbers 1, 2, so on in increasing order. And then the twos are the next smallest letters, so we put 4 and 5, increasing, and that's it. So this is the standardization of that word. And then we'll also be working with what's called super words, which have the barred letters as well. And you need to fix an ordering of the alphabets in order to standardize. So here's one ordering that we'll use. And so given that ordering, what, for example, is a standardization of 1, 1 bar, 2, 2 bar, 2, 2 bar, 2 bar, 1 bar, 1. So the smallest letter is the 1. So below that, all the ones, we would put increasing sequence. Now, the next biggest letter is 1 bar, but when you standardize the 1 bars, you standardize in the reverse of the positive letters. So they're going to be decreasing left to right. So we go 4 here and 3 here. And then the 2 is the next biggest, 5 and 6. And then the 2 bars, I think, would be 9, 8, and 7. So again gives a permutation. order preserving, but with the barred letters standardized in this reverse order. Okay, so now one way to write the LT is the sum overall sigma in Sn of, oh, yeah, times the sum overall W in A plus to the N X to the W, Q to the standardization of W. Oh, standardization of W equals sigma, Q to this, Q to the M I of sigma. So that's just going up to the original definition here and noting that you can group, because the inversion statistic is invariant under standardization, you can group all that together. And this thing comes out here, summation sigma and Sn Q to the M I of sigma. And then this thing here is one way to write the Gessel fundamental quasi-symmetric function, which usually depends on a subset of the numbers 1 through n minus 1, and in this case, it's the descent set of sigma inverse. Okay, so the Gessel fundamental is usually defined in terms of a bunch of inequalities, but I'll just use this kind of description here today. Just the exploits of all the words which are standardized to a given permutation. And it depends only on actually the descent set of the inverse. Now, superization says that if, well, I'll just say it in words. So if you have a symmetric function, which can be written in, oh, maybe I'll rewrite the sum. If T a member of sim and T of X is summation overall sigma and Sn times some constant C sigma, and let's say that can depend on a number of parameters. Today it'll just be depending on Q, times this F des of sigma inverse of X, then so I have the second part of the talk down here. I thought I'd have enough room. I see I'm not even close to having enough. So I'm going to bring this down here. Copy. So if you have that, then this identity, the symmetric function satisfies a more general thing. Um, And now we're going to use this other description of the f, summation w twiddle in. So now we have super words, a plus or minus to the n, x to the w. Okay. So this is a theorem. It's not particularly deep, but it's not particularly quick to prove either. One way to do it is to work with Schur functions. The basis for ring of symmetric functions show that for a given Schur function, so that there's a known fundamental expansion for that, and you can anyway, just state this as a fact. Okay. So what we have here, oh, and what is, I didn't write this right. Z to the W twiddle. So Z to the W twiddle is the product over all I, where Zi is a member of A plus. All right, so not Zi, Wi. Xi, and the product over all I, where W, oh, this is a twiddle. Wi twiddle is in A minus of Y sub I. Okay, so this identity is really useful in forming the, oh, there's a, I see my, what is the W? Oh, yes. Good question. That's actually not a W. It should have been an omega. Oh, now what happened? Oh, hold back. Here we go. So omega sub y is the standard involution on symmetric functions. Omega of S lambda is S lambda conjugate. And now what this means is it applies only to the y variables. And another way to describe omega is omega of the kth power sum is -1 to the k minus 1 pk. Okay, so how is this useful in the study of the chromatic? So we got this LLT pi of q to the alpha minus 1 xq. And let's just forget about that constant factor q minus 1 to the n. And you can write this LT pi of q to the alpha x minus x. Okay. And fact. So we had this, right. So if t is in sim, omega t is t evaluated at minus epsilon x. So what is that? So in Plathism, one way to define it is you take some big expression in a bunch of parameters. And say, well, what that is replacing each parameter by its kth power and fixing all constants. So if we wanted to, and by the way, these square brackets will usually indicate plethism. So if we wanted to do this, pk of negative x, you fix the, and then x usually is kind of a shorthand for little x1 plus little x2 in plethistic brackets. Then, so that's kind of your e of these x parameters, and then this would be minus p, the kth powers of all these parameters, which would be x1 to the k and so on, which is minus pk. And so a negative sign inside plethistic brackets has a special meaning. You don't, it's different from negating the set of variables, like replacing each x sub I by minus x sub I. And that's a common thing you need to do. So Glenn Tesler invented this symbol epsilon, which kind of stands for a negation of a variable. So now, because it's a parameter, you replace it by its kth power, but then you replace that by -1. So that's minus 1 to the k pk, which is omega pk. So that's one little funky little fact we need, is that the one way to write omega using plethism is to put a negative epsilon in front of a set of variables. Okay, so now we're going to do that with what we have up here. Um, this thing here is equal to, let's see now. So we want to view this as omega y applied to LT of x plus y. And I'll just put how. What do we have to specialize our parameters to? Why do we want that? Because we have a formula for this in terms of a sum over super words. Okay, so how do we get from the right-hand side to the left? Well, what we'll do is replace each x k. Let me use a different xj, say, by q to the alpha xj. And then replace y by epsilon x. Because one way to view this over here is LLT of x minus epsilon y. Okay. And if we replace the y by this epsilon x, that becomes this. And replacing the xj by q to the alpha xj gives you this. Okay. So therefore, by our theorem up there, that guy there is equal to sum over superwords so we have our z, the w twiddle. I'm going to skip a step here. So note that the there's an X weight that's very similar to all the both the negative and the negative and the positive variables have an xj, right? So you're going to get x to the absolute value of w twiddle. Replace each letter by its absolute value. So 1 bar would be replaced by 1 and so on. And then you're going to get, well, we know we're going to get q to the inv of over pi of the standardization of w twiddle. And then we've got each positive letter weighted by this q to the alpha here. So we get q to the alpha times the number of positive letters. I'll just write that as pos. And then because of the negative epsilon y, y was replaced by epsilon x here. So that gives a negative sign for each -1 to the number of negative letters. Yeah, so that's the one way to write this thing up here using the superization. Okay. And
Jim?
yeah, yeah.
In your identity, a little higher. Yeah, with LLT omega y. There is no pi. The pi is not involved, is it?
Thank you. Pi did not go away. It's still there. Okay. So let me do an example. Say we want to find LT pi. Oh, not that. So we want to find chi pi of this thing we call Q alpha. So Q alpha is Q to the alpha minus 1 over Q minus 1. So this is actually chi super alpha of a set of variables with just one variable, which is weight 1. And so if alpha is a non-negative integer, this is really a positive kind of thing, but alpha could be a real parameter. So how do you actually find this here? Okay. So what you do, so this is going to be...
Is this the same as replacing x equal to 1?
Yes.
Okay.
Right, exactly. So if we write this in terms of LTs, we have just Q to the alpha minus 1. Okay, and then there's this factor here to the n. Okay. And how do we do that? So this is a very simple example compared to what's up here. This is like letting x equal 1 in this formula. So now there's actually only two. W twiddle is in 1 bar to the n. And then we have this stuff here. So the x to the absolute value is just 1. But then you have q to the inv of w twiddle, which of course is the same as the standardization. And you have q to the alpha to the number of positives, q to the alpha pos, and minus 1 to the number of negatives. Okay. All right, so how do we do that? This is here. So we're going to think of putting a 1 or a 1 bar into each of these squares on the diagonal. Okay. Now, if you put the 1, you're going to get a q to the alpha because it's a positive letter. But we're also going to try and calculate how many inversions is that going to create in this row. And because the first 1 in this word is the smallest letter under standardization, you're not going to get any inversions. So I'll just put dashes there. Okay. So let's just say we do that. So we go on to the next one, we put a 1 bar. Then
Stand.
the heck is that? That's the Siri of my other computer. I don't need that computer, so. I'm wondering if Siri did understand the first part of the talk. That would be scary. Okay, so so if we put a 1 bar here, because so this 1 bar is going to be bigger than everything below it because of the way the 1 bars are standardized. We're working with the ordering 1 less than 1 bar here. So 1 bar is going to be bigger than any 1 below it, but it's also going to be bigger than any 1 bar below it. So we're going to get, so use the red dots for inversions. And if you think about it, wherever you put a 1 bar, you're going to automatically get inversions in everything in that row. But the things in the column above you are going to be determined totally by whether the entries in those rows are 1 bars or not. So whether a given pair of things is an inversion or not is determined by whether the upper element is a bar or not. Okay, so this, so if I call that B2, so that's a number of cells in that row, in the second row from the top, which are to the right of the path and to the left of the main diagonal. Then I can write this thing here as a product. I equal 1 to n. And if I use the positive entry, I don't get any inversions, but I do get a q to the alpha. And if I use the negative entry, I get these I different things. Okay. And each of the cells operate independently. Okay, and that's Q. I'm going to factor out all the BIs, and that's really just the area underneath the path. And product I equal 1 to n. And now I factored out the QI, so I've got Q to the alpha minus BI minus 1. And I want to divide all this in the end by Q minus 1 to the n. And so let me write this a little simpler. Q, the area of pi times product n of alpha minus BI. Okay. And I can also write this in a different way. Minus AI. So AI is going to be the number of cells in the column above an entry. Above. So one way to see why that is true is use the fact that the LT polynomial is known to be equal if you reverse the path, in which case these row numbers become the column numbers. And this way of writing it is a little more useful for me because this is what's called a rook product. So what is that? So a brief review of rook theory. So this entry, so here's a board B, and let's see CK be the number of cells in the kth column from the left. So here, C1 is 0, this example, C2 and C3 are 0, and then Cn, I guess, would be 5. Okay, so that's a Farrer's board. And there's this well-known theorem that if you take the product of alpha plus Ci minus I plus 1, then you can expand that in the bases. Well, so this is actually Q-Rook theory, which was introduced by Garcia and Remmel. And here is a Q-hit number. So that's a polynomial in Q, non-negative integer coefficients, and has a combinatorial interpretation. And another way to write this is a sum over K and alpha minus K plus 1. And there the coefficients are the n minus K Q-Rook number of the board. So I won't define these. I think Jason is going to be talking a little bit about that next time, time permitting. But if anytime we get a rook product, we can write it in terms of these bases we're interested in, combinatorially with non-negative coefficients. All right. And we're now going to use this with a different technique we call the XY technique to get some expansions in monomial basis and other bases with positive coefficients. So, oh, I should add, is there any questions about what we have so far? So we've used superposition to get a formula for the alpha chromatic in terms of sum over super words. And then we gave an example of how to specialize that to get the alpha chromatic in terms of this Q alpha, or actually the chromatic in terms of Q alpha, which is the alpha chromatic, which is in terms of 1. Okay, so up here somewhere I have, yeah. So the XY technique is, so given a dict path pi, we're going to take the chromatic in terms of a product of two sets of variables. Okay, and here XY is the set of all Xi, Yj. Okay. And how do we do that? Well, so I put these, so this like 1 comma 2 here would correspond to X1, Y2. So I put a given filling along the diagonal here. And we need, since we're working with a chromatic, it's got to be like a proper coloring in these two parameter, two coordinate colors. So this 1, 2 here, this 1, 1, so they're different. We can't have both coordinates the same if they attack the same square, but like I can have a 1, 1 here and a 1, 1 up there because the square there is above the path. Okay. So for this given coloring, the first coordinates will be the x variables, and there's 6 1s. So I get x1 of the 6 and 3 2s in the first coordinate. And then there's in the y coordinate, second coordinate, I've got 4 1s and so on. And then I'm using AB bigger than CD if A is bigger than C or A equals C and B bigger than D. Okay. And so I've got the red dots are the inversion pairs in this example. Like the 2, 4 is bigger than the 1, 2 here. And then also the 1, 3 is bigger than the 1, 1 because of the second coordinate. And I can break
Wait,
up this, oh, yeah.
pardon me, above the 1, 2 with the dot, you have a 2, 1 in that vertical run that appears to be attacking. Why don't you have a red dot there?
You mean here, this 2, 1?
Yeah.
Oh, I was just seeing if you were alert. You are alert. Thank you.
Okay.
So we got to make that a 5. Okay. Okay. So we can break this up by first just looking at the first coordinates. And these first coordinates can be any what we call lambda coloring. So now, because we're going to be putting the second coordinates in, and we can always put those in such a way that if we have equal colors which attack, then we'd have to have the second coordinate bigger or different. Not bigger, necessarily bigger, but different. Like these 2 2s, the second coordinate has to be bigger when we add that in, but that's okay. All right. But here we know for sure that if we have like this 2, 1 here, and as in Brendan's example, I keep losing my colors. Anna, do you know how to get these colors back?
Yeah, you just like click on the pen again.
So there's another one. So we can determine whenever we have unequal first coordinates, we know for sure whether they create an inversion pair or not. So we're going to get a certain power of Q from those. And then we can kind of eliminate those squares from the graph. When we add the second coordinate, we don't care about those because we know they're already going to be inversion pairs no matter what we put. But then once we put the second coordinate in, we've got a smaller thing, and we can forget about the first coordinates as far as the coloring goes and whether we get an inversion. So only the equal first coordinate edges in this graph are carried down here, and I've kind of rearranged them like the 1, 1, all the ones, these 3 1s there kind of go into this part. And then there's also 3 1s up here, which go into this, and I just kind of group these all together because all the ones, the first coordinate ones, end up creating a chromatic of a smaller graph down here. And then all the 2s create a chromatic there. So not only is this graph down here going to be a chromatic in the y variables, but it's actually a product of chromatics for each of the equal first letter edges. It's not maybe obvious totally obvious that this graph down here is a unit interval thing, but that's not hard to show. That'll be an exercise. Okay. So we now have a way of writing the chromatic in a XY as a sum of colorings of the graph with the first coordinates, this kind of object, times a chromatic in the Y set of variables. And yeah, maybe I should have written out what the actual theorem is here. I meant to. So this is equal to a sum over lambda. So we can look at m lambda of x, and then a sum over lambda colorings C q to the m pi of C. So lambda coloring is lambda 1 1s, etc. And then we have a chi times some smaller path, beta of pi, in the y variables. Let's see where we are. Doing well on time. Okay. So let's do a corollary. The Schur expansion of the chromatic, if alpha is a non-negative integer, that is positive with combinatorial interpretation. So how do we prove that? So I'm going to let x equal q alpha, I guess y equal x. So this is what I'm looking at here. And this m mu of q alpha, because alpha is a non-negative integer, this is a monomial symmetric function, a bunch of positive q powers. So it itself is a non-negative integer. I mean, it's a polynomial in q with non-negative integer coefficients. Okay. And then there's the sum over all the lambda colorings, and we'll get a certain power of q times a chromatic in the x. And Shrisian and Wax prove that this is Schur positive. And in fact, there's a nice, very elegant combinatorial interpretation in terms of certain kinds of tableau. And so you multiply all that together, and we have everything is combinatorial with the interpretation, and it's positive. Now, unfortunately, that doesn't allow us as is to see if alpha is a real parameter, this thing here is no longer particularly easy to describe. Now, and it's also not easy to expand in any of the alpha plus k choose n basis or the alpha falling by k basis. Okay. Now, okay, so anyway, that's as far as we get there. Another example is we'll expand this thing into monomials. So the scalar product of a symmetric function with h lambda is the coefficient of chi pi alpha of x, coefficient of the monomial symmetric function m lambda of x. Okay. So, and we can show this sum is not only positive, but it's a positive sum of root products. And this is true for any alpha. And that's really nice because the root products can be expanded in terms of the x plus k choose n basi and the alpha falling basi combinatorially. So to get this, we're going to let x equal x and y equal q alpha in the xy identity. So basically just letting y equal q alpha. So let's go back up here where we were up here. So if you let y equal q alpha, this thing here earlier in the talk we showed as a root product. If y equal q alpha. And everything else here is positive, combinatorial. It's a sum over all these lambda colorings, m lambda of x times. Maybe I should have made this a little clearer. So the coefficient in the lambda colorings, the x coefficient is x1 to the lambda 1, x2 to the lambda 2. And because it's a symmetric function, this will compute, the sum over lambda colorings will compute this coefficient, but that's the same as the coefficient of that in m lambda of x. So that's why we can just restrict to those particular types of colorings. Okay. So that's like the two nicest corollaries. So we have other proofs, another proof of monomial positivity by direct bijective argument. And Jae Song may be covering that next time. And also we have some results on sure things. Might mention we conjecture that the coefficient of pi alpha pi with a sure function lambda can be written somehow as a sum over t in the standard Young tableau of lambda q to just some power unknown times a root product, and we don't know, which would depend on t and pi. And this conjecture, if it were true, would kind of prove everything we're trying to prove, because we would, if we understood this combinatorially, then we would get the expansion in these two bases, the alpha plus k choose n basis, the sure expansion. We've been unable to find any patterns even for hook shapes, but we just know for small n, we can always write it in this particular way. And also, I might mention that the statistic on standard tableau, by letting that alpha parameter go to infinity, you can show that if you did write this in this way, this Q statistic would give you a way of getting the sure expansion, the sure coefficient of the LT pi. So that's that other famous problem. And so this is actually a seemingly harder problem. But sometimes harder problems are easier. We're hoping this is one of those. And let's see, so I got 5 more minutes. Yeah, I want to describe or mention that. Oh, and we also don't know how to write the fundamental. We have a way of writing the fundamental expansion for, or a fundamental expansion for chi pi using superization. And it turns out to be a product of things, kind of like the Q alpha product for the monomials, except these products are not root products. So that's an open question, which is probably something we would have to do before being able to do this. Fundamental expansions are a lot easier than sure expansions. So finding a way of running
Jim,
yeah.
I have to go to class, so I would like to ask a question.
Sure.
And if in the last green statement,
This one here or this one? This one
green,
here?
yeah.
Okay.
And have you tested this on lambda, hook shape, or staircase?
Right. So we cannot do even the hook shapes. which is a bit embarrassing. If we could do the fundamentals, if you had a general fundamental expansion in terms of root products, then just general theory will give you a formula for the sure hook shapes. But we don't have that. Yeah.
I see.
So that's kind of disappointing. You would think a hook would be something we could do, and probably it's doable. But that's maybe the next step to try and find. So anyway,
Thank you.
thanks for attending. So one other comment. So the XY identity, I wrote it in terms of the chromatics, but you could have written it in terms of just the original LT pies. And also there's a version of it for general LT polynomials. And I think I have a time to just say, so say we have, so a general LT is you got a tuple of skew shapes. Okay. And you think of these embedded in a plane, and if you have a big in one shape and a small in the other, another shape, and there's other things here, that gives a Q. Or if you have a big and a small like this, that gives a Q. So you can, so how would you take an LT here? So you got to fill each of these with semi-standard Young tableau. That's the definition of the LT. And what that means is that the first coordinates have to be what's called a reverse plane partition. They just have to be weakly increasing. And then the second coordinates have to be a reverse plane partition above those, and so on. And then not the second coordinates, the first coordinates, which have 2, and so on. So you start with something like this, and then you have to add in second coordinates. Now, as in before, all the inversions involving different first coordinates could be computed just from this diagram here. And also, when you look at so if we add in the second coordinates here, we don't have to worry about the second coordinates to say this guy being bigger than the second coordinates or than that guy, because you already have an inequality there guaranteed. So to get the semi-standard Young tableau with the 2 coordinates, each of these things here, all the 1s kind of are independent of all the 2s. And without saying any more, because I'm out of time, this will factor, you get a sum over these kind of things, and then you get a product of LOT polynomials corresponding to all the skew shapes with the 1s, that tuple, and then all the skew shapes with the 2s, that tuple, and so on. Okay, so thank you.
Thank you, Jim.
Uh,
Any questions?
Yeah, so I've got one. Thanks for the great talk. So just a very kind of broad thing. You have this very crucial Carlson-Mellet relationship between the Q chromatics on the one hand and the unicellular LLTs on the other. You talked about general LLTs at the end. If I take a general LLT and do sort of an inverse Carlson-Mellet, is there a nice combinatorial interpretation of what that might mean in terms of something like graph colorings?
That's a good question. And I was actually going to say something about that. So in the Carlson and Mellet, let me use blue. Pi. They're looking at this thing here. Now, the substitution Q minus 1, so let's say we have a general LT, and we do this. So in this proof of the modified McDonald formula, we use the fact that this thing here is a sum over non-attacking fillings. And in the terminology of graph coloring, it means proper colorings. Yeah. So you can, and that part will work for any LT polynomial. So Mark Heyman was the one who found this particular, there's a sign reversing involution, which we use in the McDonald, but that thing Mark pointed out to me that works for any LT. Okay. Now, there's another special thing though that works for the unicellular LTs. So once you've got for the unicellular, and there's this two ways to write that. In that you can write as in the general thing where you bunch of single squares in the tuples, or you can rewrite it in this thing with things along the diagonal. But for a given thing here, like we're going to put in we have this non-attacking fillings, and then we're going to put in positive and negative letters into there. And what you can do is show that when you flip the sign, if you just look at all the fillings which have a same absolute value filling underlying it, then that factors as a product of n q minus 1. It's q minus 1 to the n, because you're getting a something like you get an extra q from here, from the positive choice. You get a q because of, well, you write this as qx minus x, and you get extra q from the positive choice, but from the negative choice, because there's non-attacking, so 1 less than 1 bar, less than 2 less than 2 bar. Flipping the sign on something doesn't change the number of inversions at all, because none of these things that attack this guy here are a 1 or a 1 bar. And when it related to all the other things, 1 or 1 bar are the same. So that's what allows you to divide by this. But that's not going to work for general LTs. Now you're going to get something, a sum over super fillings, but you can't factor it as a product like that.
Okay.
So this thing here is really a kind of a special fact.
Thanks.
Yeah.
Any other questions for Jim? Or if not, let's thanks Jim again. Thank you so much. And Jason would give the last lecture of the series on Thursday. So hopefully you can join us. All right. See you guys. Bye.